All right, ready for our next talk. It's my pleasure to introduce to you Faith Oehlerking. She is an additive manufacturing R&D engineer at HC Starck Solutions. A top supplier of HC Starck is a top supplier of refractory metal products. Faith serves as the technology leader for laser. As the main programmer and operator of HC Starck powder bed machines, Faith conducts parameter development and component production of additive manufacturing refractory metals, and these are niobium, tantalum, tungsten, molybdenum, and custom alloys. Faith works with the team at HC Starck Solutions to continuously develop new additive manufacturing materials to serve the medical, aerospace, industrial, nuclear, and defense markets. Prior to joining HC Starck, Faith was a product development engineer for Formex Metals, a metal 3D printing startup developing laser powder bed fusion materials for the tool and die industry. She received her BS in metallurgical and materials engineering from the Colorado School of Mines, and also held internships at SpaceX and Howmet Aerospace. So, for Faith to be with us. Faith, why don't you go ahead and pull up your slides?
Sure. Let's see. Let me know when you can see them.
Take it away.
Okay, great. Thank you so much, Amy, for that introduction. First of all, I just want to say thank you so much for this opportunity. What an amazing conference, seen so many good talks today. So I'm honored to be here and talk about some work that HC Starck is doing. Today, my talk is about optimizing refractory metals for additive manufacturing. Here's just a quick agenda of what we'll be going through today. I'll give an introduction of our company, the refractory metals that we produce, and how we are implementing those materials into the additive manufacturing space. And then if we have time, I'll go into a few case studies of actually applications of these AM parts and move forward from there. So Amy just gave a great summary of my introduction, but I do have a background in metallurgical and materials engineering from Colorado School of Mines. My background is in materials for laser powder bed fusion platforms. I'm one of the lucky ones who got involved into the additive manufacturing industry right after school. So I'm very passionate about additive, and I'm looking forward to bringing AM materials further into the AM space. So if you're unfamiliar with HC Starck Solutions, we are now a 101-year-old company started in 1920 in the heart of Germany. We are a metal parts producer, a metal powder producer of refractory metal products. So the four main refractory metals that we are talking about here are listed below. So that's niobium, molybdenum, tantalum, and tungsten. And these metals serve various different industries, including aerospace, electronics, medical, industrial processing, and now most recently, additive manufacturing. So as you probably can imagine, we do have 100 years of experience, but not only in additive manufacturing. We cover a wide range of the value chain, all the way from metal powder producing up to press and sinter and melting technologies, all the way into the final fabricated part. Today, I will only be talking about our additive works, but just so you're aware, we do have research and development and exciting opportunities in the traditional manufacturing sense as well. So refractory metals themselves, maybe that's unfamiliar to you, or maybe you only know it as an alloy addition in other alloys, but I'm going to take the time to kind of focus on why refractory metals are so great and why they're used in probably one of the most challenging applications out there. So again, we're talking about molybdenum, niobium, tantalum, and tungsten. And they're mainly known for their high temperature properties. These are the metals that have the highest melting temperature out there, and also very high density. So another properties that also include they're very tough and very excellent strength at these high temperatures, very wear and abrasion resistance. also radiation attenuation, biocompatibility, the list goes on and on. And so as you can see from our general products and services, there's a lot of things that we can make out of pure refractory metals and their alloys, and it can serve various different industries and in vertical senses. So why refractory metals for AM? So maybe you haven't heard of refractory metals or you haven't seen them as super popular, and that's mainly because of the properties I just listed. So even though they are super strong, very temperature resistant, and they are very superior metals, that makes it difficult to process. Traditional manufacturing, you need to use press and sinter technologies or melting technologies. You need to thermomechanical process them further into bar and ingot, and then you can machine it into the final form. So with that, these materials are difficult to machine, and then therefore there's a large material loss, and there's very many processing steps. So sometimes that makes people shy away from refractory metals in the traditional standpoint. But with the progression of additive manufacturing, you really streamline a lot of those issues. So with the design flexibility, you can use less material to have an operating part. There is less minimal machining. You're using less material when you're printing these parts. There's low material waste just due to powder recycling and minimal machining also. So really when it comes to refractory metals, we really think there's an exciting opportunity for additive manufacturing of refractory metals and really expanding that metal and material portfolio moving forward. At HG Starck, we do have three main activities in additive manufacturing. One is powder development. So we can provide additive manufacturing powder in their base forms, so tantalum, niobium, molybdenum, and tantalum, but also in their alloy forms as well. We also provide component printing, so actually service printing using our internal equipment and then also with our vendor network. And then we also have extensive partnerships with manufacturing vendors, our customers, as well as research institutes to further progress our work in the AM space. So some of the materials that we provide are listed here on the right. These are pictures of our very dense spherical powders that we provide. Something that is unique to HG Starck and even within the refractory metal industry is that we can actually provide refractory alloy powders in these dense spherical forms as well. I won't list them all here, but some to note are tungsten heavy alloy, which is that acronym WHA. This is tungsten with the addition of nickel or an iron. And then also the ever increasingly popular niobium C103 that is gaining a lot of interest in the aerospace and defense industries. These are just the common alloys listed here, but we also behind the scenes are developing our own research and development alloys specifically for additive manufacturing. Just to kind of bolster our company as well, we do have very high quality on these powders, so very good chemical purity, very high flow and low oxygen, which I'll get to in a moment as why that's so important for these materials. As for our additive manufacturing technologies that we're working on, these are the four main technologies: 3D screen printing, binder jet printing, powder bed fusion, and directed energy deposition. So again, we're mainly focusing on metal manufacturing here. I won't go into what all these technologies are. I'm sure this audience probably knows as much as I do about these, but I'll going into specifically a couple projects within our case studies here. So here are two case studies that I'm excited to talk to you about today about using refractory metals in the AM space and actually producing component parts. So first I'll be talking about our tungsten in the binder jet space, and then printing of tantalum and tantalum alloys in the aerospace and defense for spacecraft propulsion. So first, I wanted to talk about the challenges for additive manufacturing with refractory metals, like maybe why this isn't one of the standard materials that you see for metal manufacturing. These refractory metals are all body-centered cubic metals. Basically, that means that they're all prone to something that's called a ductile to brittle transformation temperature. This ductile to brittle transformation temperature is just essentially the temperature at where a material turns from ductile to brittle. And it's very important to know that temperature or know this property, especially at your operating temperature, as well as where you're going to be manufacturing it as. If you look at the table below, you can see for tungsten and molybdenum, the ductile to brittle transformation temperature is very high. So that means at room temperature, these materials are going to be extremely brittle. Niobium and tantalum are the opposite. They're below room temperature, so they're going to be a little bit easier to work with in that sense. So speaking specifically on tungsten, tungsten is one of those metals that has a very high ductile to brittle transformation temperature. Usually in traditional processing, thermomechanical processing such as rolling and forging is used to decrease that ductile to brittle transformation temperature and make it easier to work with. But unfortunately, with additive manufacturing, we're printing at the near net shape. So we don't have that option to mechanically process or cold work or hot work these materials to make them more workable. So one thing to consider is that all of these AM metals will be in melted or as sintered condition. Another thing we really need to keep in mind is interstitial impurities. So we're talking about oxygen, nitrogen, hydrogen, things like that. That will actually even increase the ductile to brittle transformation temperature even further. So really need to be aware of that in all printing environments. So this is an example of printing pure tungsten as it is on a laser powder bed fusion platform. So there has been some results out there. Complex geometries with high theoretical densities have been successfully printed, but all known examples contain some level of microcracking, as you can see in the bottom right pictures. So even though you can print parts, the parts that you're printing will have low mechanical loading. They'll just break if a lot of mechanical stresses are on them. So there are applications in this form. Specifically on the left is the tungsten anti-scatter grid collimators. These are used in medical imaging such as CT scanners and is great for the radiation attenuation property, but not as much when you're in a very high loading environment. So HG Starck, we kind of looked at what other strategies do we have to make tungsten successful for additive manufacturing. So since we know that we need to work with materials that are ductile in the as sintered or welded condition, we need to figure out another way to lower that ductile to brittle transformation temperatures. So one strategy to do so is alloy additions. So specifically talking about tungsten, tungsten heavy alloy is a good alternative. So again, tungsten heavy is the tungsten with the addition of nickel or iron. Also rhenium, which is another refractory metal, but is very ductile, can be added as well to increase that ductility. Again, I'm going to bring in the control of interstitial impurities. So now it's extremely important to work in a low interstitial printing environment. So making sure that when you're printing, you are in an inert atmosphere as low of oxygen content as possible. Another strategy that we have implemented is using a reducing atmosphere when you're using sintering technology such as binder jet or screen printing. So instead of actually using an inert atmosphere, you're using a reducing atmosphere to even to remove as much oxygen out of the system as possible. So here's some examples of where we've demonstrated success. We were able to produce very spherical pre-alloyed tungsten heavy powder. And using our knowledge of traditional processing of tungsten heavy alloy, we were able to produce binder jet parts with very full density, up to 99.7% dense, with only 17 to 19% shrinkage. Here's just an example of the microstructures, as you can see below, comparing our binder jet tungsten heavy alloy microstructure to traditional tungsten heavy alloy. As you can see, they're very similar, and so that also translates into the mechanical properties. So both in the sintered and the heat-treated condition, our tungsten heavy binder jet solution meets ASTM standards with a little increase of strength and ductility after heat treatment. So this is very great opportunities here moving forward into some applications. One of them is continuing within the radiation kind of market, using our kind of knowledge on tungsten heavy alloy and being able to sinter it to full density. Some other applications can include convergent beam collimators, radiation shielding parts, etc. And I think there's also opportunities in the aerospace and defense industry working with tungsten heavy alloy. So really we're just scratching the surface with this material in additive manufacturing, and we're really excited to bring more of it into the AM space. So next I'll be talking about our work in laser powder bed fusion, tantalum and tantalum alloys, specifically for spacecraft propulsion. So HT Starck, we are part of a kind of a group, a consortium called the STAR project. STAR stands for Super High Temperature Additively Manufactured Resistojets. So resistojets are a very specific method of spacecraft propulsion. It's actually very popular for our satellites. And the goal of this group is to design a single component, which you can see here on the right. That's a cross-section of the component that has very complex geometries. So this has nested and interconnected heating elements, very fine details, very thin walls, but they want to be able to print this with the highest melting point materials on Earth. So therefore, refractory is a solution here. It's difficult to find any other technology or any other materials that really meet this design requirements for this project. So this is a great consortium that we're happy to be a proud of. We are supplying the materials. Hyeta with their Renishaw machines provided the printing, and University of Southampton, there's a researcher there who really is driving the work of the design and also the testing as well. So as I previously mentioned, tantalum is a refractory metal that has a low ductile to brittle transformation temperature. It was below room temperature. And so therefore it can be easily processed using laser powder bed fusion technology while still maintaining its high temperature resistance in the as printed state. So we decided to bring tantalum and provide tantalum and tantalum 10 tungsten. So adding tungsten to the system also can increase the strength even further to reach those high temperature strength targets that the resistojet needs. This is just some of the work that Hyeta did on their Renishaw AM500 machine. So even though that these tantalum materials have very high melting points, you can use standard powder bed fusion platforms with the regular 400 watt laser to create densities greater than 99.5%. This is extremely important because being able to print at such high densities really reduces the amount of post-processing work needed for this application. No hipping was needed to get to this density, so very printable as is. They further did some parameter development on single track work to really hone in on the dimensional accuracy on those thin walls. And they were able to achieve under 300 micron single tracks that were dimensionally accurate, which is very great. And with all that work that they did, they were able to print the tantalum and tantalum 10 tungsten resistojets in their full completed form. I think they were just able to print, remove from the build plate, and send off for testing. So very streamlined manufacturing for this application, which I'm very excited about. So this is where we are currently. Currently, these resistojets are being tested internally at the University of Southampton. The main things that they are testing here is material property testing, such as emistivity and resistivity at those elevated temperatures. And also they're doing max heating tests and fatigue cycling tests at the operating temperature and max temperature. So when I'm talking about max temperature, I'm thinking 2500 Kelvin. And then also these cyclical temperature tests are meant to show the degradation of the resistor jet over time. And so these components will go through over 4,000 cycles and over 100 plus heating hours. So although this work isn't completed yet, we really think that this application has a lot of potential. After this testing, there's a full qualification campaign happening next. And then hopefully we really want to demonstrate a star resistor jet in orbit on a flight demo mission, earliest 2022, but it's coming, so keep it on your radar there. There's just to kind of sum up other opportunities we think that tantalum and also niobium alloys have in the aerospace and defense market. Really using the benefits of powder bed fusion, you can really design and create these high temperature rocket nozzles with very thin and intricate vanes, maybe some conformal cooling. And I think we're really, again, just scratching the surface of what refractory metals can do with additive manufacturing. So just to wrap up here, the main thing I wanted to bring to you guys is to bring awareness to refractory metals. I hope if you didn't know what they were, I hope you know what they are and how great of a material and all the benefits that they can provide. Using additive manufacturing techniques, they do tend to produce properties that are similar to the as welded or as sintered materials for refractories, but without the large material waste or long machining times as traditional products typically use. So using our knowledge of alloying and also controlling the interstitial environments, they have proven successful to optimize refractory metals in certain applications. And so really, I want to kind of bring about here that being able to 3D print refractory metals allows for true optimizations using the best material for the best additively designed products. So I think as an industry, as a group, we really think about how the design needs to be started from scratch, which is totally true, but I also challenge everyone to think about their material choices as well. Starck and other AM material companies out there are bringing new material solutions into the AM space. And so I think we're just really pushing the boundaries of how high performing a part can be. So I encourage you to think of refractory metals in the future. And with that, I just want to thank you. Starck is a sponsor at this event. We are located on the main stage on level 3. So I'll be grabbing lunch here in just a sec, but I'll be hanging out there. We also have some other wonderful ladies of Starck manning our table as well. So if you have any questions, you can head to the table or you can use my email there or reach out on LinkedIn. But again, just thank you for this opportunity and be ready for questions.
All right, thank you so much, Faith. And just as a reminder to the audience, obviously you can't access the main stage button when we're in presentation mode. The link on top. But we have another panel after this, so hope you'll stick around. We have lots of questions, Faith. It was such a great presentation. I think there's a lot of interest in this area. You know, I'm interested. I don't know if you saw my talk yesterday, but we have tried to binder jet and infiltrate tungsten. It didn't work out so well. So that's really neat that you can do fully dense with binder jetting. So yeah, first question is from me, and it got uploaded at first. What binder jetting equipment did you use to print that tungsten?
So this is through X1. Yep, X1 Innovative Plus system. Yep.
I had a suspicion. All right. So I think this has to do with powder bed fusion. Are there problems with build plate removal due to the parts being brittle at room temperature, and how do you address that? Yeah,
so really with build plate removal, especially on those tungsten parts, that's definitely something we keep in mind of. Even just transporting build plates can be something we need to be extremely careful for. It's just right now we don't have a specifically optimized solution. We're just extremely aware of being careful about it. More so on the powder bed fusion side, I'm working with those more ductile materials such as tantalum and niobium, so that's not necessarily an issue that I've had to run into just yet.
What oxygen levels, parts per million, have you achieved in the powder bed fusion? What reducing atmosphere do you use?
So oxygen levels, that's really limited by the printer itself. So one of the reasons why we've chosen Renishaw is because they have a vacuum pulled system where it pulls all the oxygen out and then floods with inert system. So right now, we're trying to work below 500 ppm. I know there's other machines out there that can go even lower, but it's just using that vacuum in the powder bed fusion systems is definitely key. With reducing atmospheres for binder jetting, it definitely depends on what material we're using, but for molybdenum, using hydrogen instead of argon, for example, is typical to industry standards.
Do you have any insight on how refractory metals compare to metal matrix composites for high temperature
Oh
applications?
man, you know, that is definitely a good question for Elementum 3D. I know they're doing a lot of work in metal matrix composites. I haven't done myself any direct comparisons between the two properties, but definitely we have a close relationship with Elementum. So if you have a specific interest or question about it, feel free to reach out to me and we can work together.
Awesome. And I accidentally erased somebody's question. They're moving around as I'm clicking. So if I erased your question, please ask it again. You had mentioned that post-processes are not available to increase the mechanical properties of refracting metals. Would HIP or heat treat not help? If so, why?
Yeah, so mainly when I'm talking about those post-processing, I'm talking about thermal mechanical processing, such as rolling and forging. Hipping is definitely something we're looking into right now. Those investigations are just starting, but if we're able to achieve high density as it is, we're trying to avoid the hipping process if possible. But if we do have a system with lower density, if like on the binder jet side, other than our tungsten heavy, hipping is definitely something we're looking into.
Great. Powder size distributions were listed as only 25 to 35 microns. Is HC Starck able to easily produce powder over a wider range of sizes?
Okay, so that really should have, maybe that was a mistake on my part or a typo, but we do provide this typical range of PSD, so minus 45 plus 15 micron for our powder bed fusion systems. We can go higher for directed energy depositions as well. Some of it, there are some challenges sometimes going larger. So if you have a specific request, just feel free to reach out and see what we can do. It also depends on the actual type of refractory that you're looking for as well. But we do try to provide a wide range of different dense metal powders for you. Oh, Amy, I think you're frozen a bit there, or maybe I am. Okay, I can't tell if I'm the one who's frozen or Amy is. Okay, thank you. Maybe I will I can look at the questions as well. Oh, hi.
Hey, sorry. We'll see if we can get Amy back there. Let me see if I can find some questions here. We've got time for just a few more. Can alloys be made by mixing the base metal powders?
Sorry, can you repeat that?